Okay, so welcome everyone. Today we have Asaf Inbal from Tel Aviv University. Asaf did his PhD in Caltech and then his post in Berkeley, and he is for many years already in Tel Aviv, right? Okay.
6 years.
6 years. So please take the lead.
Okay.
Yeah. Thanks.
This is working. Thanks, Neta. Thank you for the invitation. Good morning. So I'd like to present a work that I've done over the last year, which uses seismic data to reveal the motions of Hamas before the attack on October 7th. The work has been recently published in an SSH journal. This was the original name, including the word terrorist. I was required to remove the word terrorist from the title, from the main text of the paper, and change them with Hamas or militants. And I also had I dedicated the work to the victims of the attack and in the acknowledgements, and I had to remove that dedication as well. So it was very hard to publish it, but in the end, I think I was persistent enough, and they agreed. So it's available now online. So I'd like to start giving an overview of anthropogenic noise and its expression in seismic records. I usually work on data from earthquakes. I try to understand seismic sources and locate them and reveal their or the underlying physics. This is most of my work is focused on these kind of tasks. Here I switch the lens a little bit, and I'm looking at the noise generated by anthropogenic sources and what this noise can reveal on patterns of human activity. So I'll give some examples of for this kind of use cases, and then I will focus on the Gaza data set. So this is a broadband spectrum of seismic noise. The long period portion of the data has been routinely used in seismology, in ambient noise seismology, to study the structure of the upper crust or even the mantle. Most of the information here, most of the signal is generated due to the interaction of oceans with the solid earth. So these are very long periods that go down to hundreds of seconds, mostly surface waves. I will explain what these waves are in a second. The work that I will show today is focused on these type of periods, so periods that are shorter than a second, up to about 10 hertz or so. Most of these data are dominated. About 99% of these data, especially in urban areas, are dominated by cultural activities. Motion of traffic, trucks, trains, industrial activity. All these types of activities generate seismic noise due to the interaction with the Earth's free surface and are recorded by highly sensitive seismometers. And because we have a certain pattern of activity during daytime and nighttime, weekends, etc., the noise reflects these activities, and I will show some examples to this type of behavior in a second. First, the types of seismic waves the main types of seismic waves that we're going to use here are body and surface waves. The first class are waves that travel through the interior of the elastic bodies, in this case the Earth. And the second types of waves travels at the Earth's free surface. These are generally divided into two main parts. The Rayleigh waves, they generate motion in a direction that is parallel to the propagation of the wave. and loud waves induce motion in the transverse direction. Okay, so I will show some examples of these two waves. Now they are generated due to anthropogenic activities. They decay much slower than body waves with distance, which is why they usually dominate the records that we observe seismically. So what are the characteristics of these cultural noise sources? Most of them, as I said, appear at frequencies above 1 hertz. And the signals, the temporal signatures are quite diverse. Some of them are spiky, for example, explosions, and others are quite emergent. They seem like the seismic noise may blow up and decay. They could have durations of minutes or more, depends on the source. And some of them excite waves very efficiently so that they can be loud enough to be recorded tens of kilometers from the source. For example, large freight trains or wind turbine activity. This type of sources can be recorded at very large distances, tens, even 100 kilometers. The importance for earthquake seismology is usually we try to remove these effects because they mask weak seismic sources. So I will briefly talk about that, but this is how we tend to understand the noise. We have to come up with noise model and models and understand the noise characteristics so we don't flush away the weak tectonic sources that we are looking for. So this is how we understand tend to investigate cultural noise sources. They provide some information on the crustal structure. These high frequency waves usually sample a very shallow portion of the crust, so they're used sometimes used to understand the shallow subsurface. And they provide information on human mobility trends, and I will give some example from Tokyo and Meron, the Meron Hilula. And in the last portion of the talk, I will talk about how these can be used forensically for Gaza in this case. So first, the earthquake perspective and how we got to look at the kind of noise and how these kind of noise sources impact the records. I'm contrasting here two areas, one in the LA area, the Newport Inglewood Fault, and the other in the San Jacinto Fault in Southern California. San Jacinto Fault is the most seismically active fault in Southern California. And here I'm showing earthquake counts versus magnitude for these two areas. The size of the areas is similar, a couple of tens of kilometers. LA has about 180 stations, and the San Jacinto Fault routinely has about 40 stations. You can see that the curves start bending at different magnitudes. The inflection point here is termed the completeness magnitude. This is the magnitude above which the local network records all the records and registers all the earthquakes. So the completeness magnitude in the San Jacinto Fault is one unit smaller than the LA area, and although there are much less seismic stations there, and the reason is the lower level of anthropogenic noise. Okay, most of these events, the events at around one magnitude unit, are masked by anthropogenic activity, so they're not recorded very clearly in LA, but they are in the San Jacinto Fault. So this is the effect on the completeness, and the second effect has to do with the location uncertainties. This is an example of an earthquake that was reported to be located on the San Jacinto Fault, and we found that had actually occurred in the LA area, so 120 kilometers away. And the reason is that most of the station in LA area, this plot shows seismograms as a function of distance from the source. Most of the stations here, there are about 100 stations here. they show signal-to-noise ratios that are smaller than 1. They don't show the seismic rate. So when you step out of the LA basin, which is quite noisy, you can start seeing these records in stations that have lower ambient noise levels, because generally the anthropogenic noise decays slower than the waves generated by these earthquakes. So they are recorded quite clearly at large distances. So this is the second effect that brings us to work on this type of data. And this is an example of yet another anthropogenic source. It's a large explosion that occurred in southern Lebanon on October 26th. It actually was flagged as an earthquake, and the Geological Survey issued a warning for an earthquake for this explosion. You can see how it traverses the entire Israeli seismic network. This is distance versus time. These are P waves, body waves, propagating from northern Israel, Misgav, to Elat. There's a very strong phase here. It's a P wave that bounces off the Earth's maw that starts appearing at regional distances, and these are the slower Rayleigh waves that appear after the body waves created by this explosion. So this is a second type of source. A lot of the forensic seismology studies were focused on understanding explosions, detecting them and locating them, especially for monitoring of nuclear explosion. And here I will show different usages of this type of data. So one very remarkable effect of anthropogenic activity on seismic records come from the COVID. All right? So this is a very interesting study that was published a few years ago. What is shown here are seismic amplitudes as a function of time in about 200 cities worldwide, from Taiwan. Well, you can't read the names, but most large urban centers globally are plotted here. Most of them have at least one seismic station, so these stations measure the seismic amplitudes continuously, and the stations are sorted with respect to the time the COVID lockdown came into effect. So you can see how the amplitudes are muted. There is a global quiescence that takes effect right after the lockdown comes into effect, and you can see it in many places. You can also see shorter intervals that are related to activity on the weekends. So these areas are Saturdays and Sundays, where reduced activity also reduces the noise level, and Christmas is also highlighted here. So yeah.
Sorry, just curious. It's hard to say, but how much? What's the factor of between these two times? Factor in that amplitude.
So this is 1.5. They normalize by the background, so it's about between 100 and 150% difference between the yellow colors and the blue colors, relative to, say, typical noise levels. And so there was an attempt here to tie these data to mobilities. Okay, what type of activities were reduced, and this is, or changed during COVID, and this is seismic noise changes versus mobility change. The different colors are related to different activities, residential, workplaces, transport, and the best correlation was found with retail and recreation. So a reduction in mobility causes a reduction in seismic noise level. The caveat here, the main issue are these data. These data come essentially from apps monitoring, tracking where people are, so they're relatively biased. So we'd like to see there are ways to extract patterns of human activity in ways that are not as biased by the apparatus used to record or register the location or speed. So I will show some of that in a second. And I would like to focus on Tokyo. Why Tokyo? Because first, it's perhaps the largest megacity in the world, of over 20 million inhabitants. It is seismically active. It sits right on top of an active plate boundary, and it's one of the best monitored urban centers in the world. There's a dense accelerometer network that was deployed in Tokyo actually in 2008, but the data are available. It records continuously at over 300 sites. Most of the sensors are located at local schools, in backyards. And so this provides a wealth of data that we could use to study the change or the relation between seismic amplitudes and human activity at fine temporal scale. So we want to go down to scales of sub-daily or hourly levels rather than daily or weekly changes. So this movie I will show now shows the amplitudes in Tokyo normalized by, say, Sunday. You can see how amplitudes go up and go down. This is Monday just after Christmas, the week after Christmas, and then the city goes red because people drive and use trains and trucks go in and out. And then during night times it goes blue because most of the activity resides. And so these type of variations are important, and for us as seismologists looking at the effects of anthropogenic activities. And what I'm showing here is a stack of 300 stations. Again, these are the amplitudes. Here they are normalized by the levels on Sunday. Okay, so just one day on a typical week in Tokyo. And this is an average of all these traces. So each line here is, in this metric, each line is for a station. There are 24 hours here. And you can see, this is local time. You can see how the amplitude go up during the day. They drop during lunch break. They go up again, and then they drop during the tea break. Okay, Japanese break for tea at around 3 o'clock, and that occurs almost everywhere in Tokyo, and that reduces the amplitudes. And there's another more subtle change that I would like to look at, or to show you. This occurs at slightly lower frequencies. You can see this bump here. Again, the lunch break reduction, and this reduction at about between 5 to 7 in the morning. We were quite surprised to see this kind of reduction, because you would imagine the noise would just continuously grow in amplitude at least about noon. And it turns out that this reduction is actually, there's no noise reduction. There's another source. Sorry? These are trucks, yeah. These are trucks coming into Tokyo very early in the morning. These trucks generate the bump, the extra amplitude just before school starts at 8 in the morning. And so we cluster these records inside Tokyo. You can see that most of this spectral bump at 4 to 5 in the morning comes predominantly from this area. The industrial area in Yokohama is less affected by this bump because there's continuous industrial activity there, so you don't expect to see an increase. And areas here which are more rural, or less urbanized in Chiba, they show a very different trend. Very early in the morning, people at around 5 a.m., people go on take their cars and travel to work, or go on trains and travel to work. So this starts increasing at about 5 in the morning. So we can start seeing very clear patterns and divide the city into areas that are, reflect different cultural habits or different anthropogenic behaviors, and that are expressed very clearly in the seismic noise levels. Another thing that is interesting is tying the seismic amplitudes to traffic velocity changes. So these are amplitudes, again, normalized by the background, say on a Sunday. These are traffic velocity changes in percent, and you can see a very clear scaling between the two. So essentially, you could use a set of sensors along a highway to monitor mobility on that highway, which is a very nice result, especially if you're worried about anonymity. If you are looking for methods that are non-invasive and that are not affecting people's privacy, because these data do not contain any information on any other information but the seismic records. Plus, they have relatively large radius, so we are exploring the usage of these techniques for, say, tracking traffic in, say, smart cities. So from Tokyo, I'd like to bring us closer to home. This is footage from Meron. So each year, Meron hosts a very large event, Hilula. For those of you who don't know it, it's the largest outdoor event in Israel. The cemetery at Ramon, the tomb at Meron hosts about 100,000 Hasidic Jews for these festivities. The traffic around the site is blocked, and the people there, they spend the night in festivities. They jump up and down. They generate quite a strong seismic signal that can be detected by stations near Meron. So I'd like to show you how these data appear. This is a map showing the site, the area where the crowd resides is here. This is Meron, and this is the area where most people gather during the festivities. And there is an array, a seismic array that is installed in Meron. This array has been recording continuously for over 20 years, so there are many festivities that have been recorded here. And the array can be used to assess the effect of the gathering in Meron on the seismic data, to locate to track the activity in Meron and tell us interesting things about what's going on there. So I will show some examples. This is a spectra from one of the stations in the array. This is before the 2021 Hilula, and this is at the night of the Hilula. I will change that again. The scale differs, so this goes up to 150, and this is 400. You can see this very strong peak that appears between 1 to 3 hertz. This signal is a very narrow band signal that is generated due to people jumping up and down and moving in the site of the Hilula. On the seismograms, this is how this looks. These are 15 seismograms from Meron in the week before the Hilula, and this is on the week of the Hilula. You see the very strong signals that starts quite abruptly, and we can tie this signal actually to events occurring at the tomb. We know when they start lighting fires there, and when there are videos, so we can validate, say, the emergence of the seismic records with actual other sources of data. We use the array to pinpoint the location of the crowd. We run array processing techniques on these group of sensors. The details are less important, but I'll just show you how these appear. So this is one record before we filter and after we filter. This is the raw data and the filter data in blue. This is the correlation between the stations, the average correlation between the array stations. Okay, the correlation tells us the level of waveform similarity. So the actual activity generates highly similar signals between the stations. I remind you that the stations are quite close to each other. The configuration is such that there's only about 50 or 80 meters or maybe a kilometer, up to a kilometer between the nearest stations. So this dictates high level of similarity between the stations, which allows us to pinpoint the location of the source. This is the back azimuth. The back azimuth tells you the direction pointing from it's a vector, pointing from the array towards the source. So this is the back azimuth during the festivity. It is quite stable, and it points to the location of the festivities, and the slowness, which is 1 over the surface wave propagation, is also quite stable, and it averages to about 1,000 meters per second, which is the expected speed of surface waves at these frequencies. We can contrast different years. 2018 is a typical year. I'm showing here the nighttime amplitudes for 2 weeks before and after the event at Meron. You can see this very strong peak at the night of the Hilula. It really stands out. It's a very unusual night in those data. And the two lines represent two different stations. One is close to the site of the festivity, and the second is far from the site of the festivity. And as expected in 2018, the station near the Meron site shows higher amplitudes, because as I mentioned, the amplitudes, the waves decay with distances, so the station that is farther from the site has a lower amplitude as expected. 2021 was an unusual year because of the crowd crash. For those of you who know this event, it was a catastrophe at Meron. And here the amplitude switch, and the reason is that this station, the blue line, represented by the blue line, is situated near a highway leading to Meron. So it is recording a large number of vehicles that are traveling to the site right after the crowd crash, which is why it shows higher amplitude than the station near the tomb. And this is the COVID year, where we see a very weak signal from the site. There were only maybe 100 people there at that time. So we compiled a number of data from different outdoor activities in Israel, including marathons, outdoor events like navigational events that occur near seismic stations. We know we can estimate the number of participants in each type of activity, and we can build these semi-empirical crowd attenuation curves. So there is a very nice scaling here between the crowd size and the amplitude corrected for the attenuation due to the distance from the source. So they fall more or less on one line. We have here events that have few hundred people up to the largest event in Meron that has about 100,000 people. So this type of scaling tells you, given a distance to the source and the amplification number, amplification factor, again, the amplitudes here are normalized by the background, so how much above the background you record the signal. That tells you the number of people that are gathering in a certain area. This has several interesting implications on the noise levels and the effect of activities on seismic records. So I think I can now transition to Gaza. I hope I convinced you that human activity has a very strong imprint on the seismic records. And so let's see how the Gaza data set shows what happened at the morning of the attack. So we have footage of Hamas militants boarding light vehicles, bulldozers, and moving in the early hours of October 7 towards the border with Israel. We know that there was a large, we don't know exactly how many people moved there, but there was a large group of people that moved towards the barrier breach points. And on the Israeli side, there was zero motion, almost. All right, Saturday morning, Simchat Torah, very quiet time. So there's a highly anomalous activity on one side and a very low level of activity on the other side, and that gives some hope that the record from the morning of October 7 can be detected by the seismic station. And on top of this above ground activity, we know that there is some underground motion taking place in the tunnels, so this would also generate loud signals that we expect to see at these stations. So to summarize, this commotion, this activity is supposed to provide a signal that is detectable. All the records that I will show, all the data, all the analysis that I will show focuses on the time before the first rocket was shot. Okay, there are no fires or rockets at the records that I analyze here. So essentially, this is the case. I think you already understand it. This is a regular day. This is the day of the attack. We have an increase of noise, plus we have perhaps some instances, short intervals that contain coherent events that can be detectable across the network, and I will show that. Fortunately, we don't have data from stations near the Gaza Strip. So we are using 3 stations that are located quite far away from the Gaza Strip. One at Amatzia, the other at Yatir, and this one at Tziot. Yes.
The Nova party, which was probably a big
Yeah.
mass of people, it didn't affect.
Yeah, we looked at it's a good question. We looked at the records from other festivities, outdoor activities, and we found that they didn't create the type of amplitudes that we record on the morning of the Gaza on October 7th. So they do generate seismic amplitudes that are noticeable, but not at those distances. Okay, that's a good point. Actually getting information on the number of participants and location of past outdoor festivities such as Nova is difficult. It was difficult to find how many people were there, where they took place, but we managed to do that. So this is the record from Yatir. This is time, local time, and the colors correspond or represent, are like a proxy of how anomalous the signal is. So this, or what is the probability that the signal is unusual. So This is early hours, and then the attack started at 6:30. This is when we detect the attack at the 3 stations. As you can clearly see these arrivals at Yatir. And this is the farthest station from the strip that is being used in this study. It's about 55 kilometers from the city of Gaza. So quite loud, high amplitude signals at about levels here are about 10 to the minus 8 meters per second. These amplitudes are below the resolution of optic fibers. For those of you know the type of records that Tzachi is analyzing, these signals would not show on optic fibers. But they do on these highly sensitive broadband stations. This is the spectra, the background, and the day of the attack. You can see a sharp peak at a very narrow band frequency range between 5.5 to 6.5. This is generally the frequencies that are seen when we see vehicular activity at recordings at these type of distances, tens of kilometers from the source. And these are the 3 stations. The solid white lines are the lines of October 7. You can see all 3 stations correlate quite well. They all start jumping at the same time. And they all arrive at relatively high amplitudes. They're in the 90 or 95 percentile of all the past Saturdays. These are the dashed lines here. So we compute the reference noise model there based on all past Saturdays in the 3-4 years preceding the attack. We looked at the data from all past Saturdays. We didn't find anything that looks as the data from October 7th. So this is highly unusual. This is the correlation between the stations. They are well correlated, which is also highly unusual. You don't expect stations that are 50 or 80 kilometers apart to be correlated at these at levels of over 90%, because these waves are very short, have a very short wavelength. The 2 to 6 hertz wavelengths that we analyze here are the characteristic wavelengths are of the order of a few hundred, maybe 100 meters or so. So on a regular day, there's no correlation between station in Tziot and station in, say, Yatir. But on the day of the attack, because there was a single or an area producing very loud noise, these 3 stations are highly correlated. And you can ask these statistical questions of what is the chance of getting this type of amplitudes over a certain amount of time, and this level of correlations. The chances are very, 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 very low. If you just look at the noise and you ask yourself what is the probability of seeing this type of correlation by chance, the chance that you would see this kind of, that a random signal would give rise to this type of correlation is, the return time is about 15,000 years. So on a geological scale, you might be able to see this kind of correlation by chance. So highly unlikely that these records do not reflect activity in Gaza. Plus, we don't have any source in Israel that could give rise to these kind of correlations, okay? The second thing we wanted to do is to locate the signal. So we use the 3 stations. We use an array analysis approach on the 3 stations. This is a sketch showing the approach. The interstation arrival times can be used to pinpoint the source. Plus, we can rotate the horizontal axis, the horizontal channels in each one of the stations to maximize the level of correlations. As I mentioned before, the Rayleigh waves are polarized in the radial direction, the direction of propagation. So you expect that once the horizontal channels in each station point at the location of the source, the correlation between the three stations would be the highest. So we look for relative arrival times and rotation, interstation rotation angles that maximize the correlations, and that gives us two independent measures of the location of the source. One comes from the interstation arrival times, and the second comes from the intersection of the polarization vectors. Okay, and we use these measures of the sum of time delays. So the sum of time delays, station 1 to 2, 2 to 3, minus 1 to 3 must sum to 0 for a perfectly coherent source, and same from the interstation rotation angles, and that gives us a measure of the quality of the detection. And we use this type of analysis to locate the source. This is an example of a sensitivity or resolution test. We only use sources that have travel time residuals that are less than 0.5 seconds. So these are contours showing travel time misfits. And the way we do the location after we recover the station time delay is that we assume the sources are located along the Salah ad-Din road. Okay, we constrain the location to be along the Salah ad-Din road. And why? You see that the stations are far from the Gaza Strip, so and they are asymmetrically distributed with respect to the sources. So we don't have resolution in the direction along the narrow axis of the strip. We only have resolution along this line. The second reason is that Salah ad-Din is likely it's a major highway crossing the strip, and it likely hosted many of these vehicles. So we solve for the location along the Salah ad-Din road and for the surface wave velocity. And so these misfits show you what is the travel time. This line shows you what is the travel time misfit you would get if a source was located here, but you constrained it to be on the Salah ad-Din road. So these are 1 second. So all the sources that we analyze have misfits that are lower than 1 second. So they are highly, most likely coming from within the strip, but we don't know if they're near the eastern or western portion of the strip. In terms of the resolution, we have a resolution of about 2 kilometers in the direction along the Salah ad-Din road. Okay, and these are, as I said, we saw for the location and for the surface wave velocity, so we can validate the velocities that we're getting. The surface, we assume a uniform surface wave velocity for the 3 stations, and the velocities we're getting are about 1 kilometers per second when we use impacts from bombs dropped on Gaza to validate the speeds. So this is one example of traces from one of these airstrikes, and it shows that the waves travel at about 1 kilometer per second, which is consistent with what we get. And this is a zoom in on the records. What you see here are the correlations and the effect of optimizing them with respect to the non-optimized correlation. So they jump by about 10-20% at times. And these are the quality factors. I'd like to, I won't go into the details here, but when you zoom in on these records, there are short time windows of about 1 or 2 seconds that are locatable. Here you can see about 10 of them, and out of these 10, about maybe 5 time windows also give misfits, travel time misfits that are less than 0.5 seconds. So they're highly likely to be coming from Gaza. And when you, after rotating and aligning the seismograms, you can see that the three traces follow each other wiggle by wiggle at times. So they're not as correlated as we would see for tight configuration of arrays recording earthquake signals at far away, but they are well enough correlated to be locatable. And at these times, they also show amplifications that are maybe 10, 20, or 30 times the background level. So the detections, we think, are quite robust. So I'm plotting here the time-space distribution of the detections. This is location along the Salah ad-Din road. This is time. And these lines correspond to sources propagating at between 25 to 50 kilometers per hour. So these are velocities that are consistent with the motion of heavy vehicles, bulldozers, or convoys that travel along the Salah ad-Din road or along the northeast and southwestern axis of the Gaza Strip. And the colors here of these polygons represent the times during which each of these area was active. So area A, just north of Khan Yunis, was active for 30 minutes. And area C was active between -20 to between 10 past 6 to 6:30, as well as polygon B, and polygon area D was active only 10 minutes before the attack. And so our interpretation for these results is that we're seeing convoys or groups of vehicles that leave the Khan Yunis area towards the northern and southernmost portions of the Gaza Strip. Once we start seeing signals from the northernmost area of the strip, so near Bet Lahia, this is just 2 to 3 minutes before the attack commences, before the fence was actually, or the first rockets were fired on Israel. So there is there is no signal coming from northern Gaza before about 6:26. So this is, we think it represents the motion of Hamas in the minutes preceding the attack. And the last thing I would show you are the polarization angles. So I mentioned that we have independent measures of the location, one coming from the interstation time delays and the other coming from the polarization vectors pointing at the source. So these are, this swath represent the distribution of polarization angles from the three stations. So at Amatzia and Yatir, we are seeing mostly Rayleigh waves in these directions. And at Ktziot, we are seeing mostly love waves. Ktziot is mostly sensitive to love waves, so the direction is normal to the direction of preferred polarization. And the three the polarization vector from the three stations intersect on the Gaza Strip. So this is this serves as another line of evidence for the robustness of the locations that we get from these three stations. Yeah, so this is a summary of my talk. I think the most important, or the most important point is that the detection was made possible because it occurred on a Saturday morning, where if the Hamas had attacked on Tuesday mid-noon, we wouldn't be able to see them moving seismically. Okay, so the low level of seismic noise on the Israeli side versus very anomalous levels of activity or seismic records on the Gazan side, this is what allowed this type of detection. We were able to pinpoint locations along the Salah ad-Din road, showing how terrorists propagated along the extent of the strip before the breach took place. And we think this is related to large-scale, this type of mobilization is related to a large-scale motion in Gaza, coordinate motion in Gaza before the fence was breached. And we know that the attack commenced simultaneously along the fence. So the fact that we're seeing signals coming from everywhere along the Gaza Strip at about 6:26, 6:27 is consistent with the observations from the morning of October 7. I will finish here and I'll be happy to get your questions. Thank you.
Questions?
Thanks so much, Asaf. I'm not sure if I understood correctly. You said that you deduced the speed of the waves is about 1 kilometer per second?
Yeah.
Of the station? You have to deduce it? It's not a known thing?
Yeah, it's there are studies using seismic data to recover the Earth's velocity structure. So you could use the velocity structure, if you know it, to locate the source. In this study, we didn't want to do that. We didn't want to assume some velocity, partly because the velocity structure is not very well constrained in that area. Okay, there are very few stations, normally only 3 in all of the southern Negev, so the velocity at the large distances is not very well constrained. So we said we will solve for uniform velocity and for the location. And then we will try and validate that velocity with known impacts in Gaza, which is what I showed at the second step.
By how much can it change normally? The speed of the waves?
It depends on it's depth dependent. So these waves, but it could change by tens of percent from the uppermost part to a depth of a kilometer or so. This is actually where the portion of the crust where the wave speeds change most abruptly. When you go down to larger depth, the speeds are more constant. So, yes.
Thanks.
Yeah.
How did you make your map with the contours of the travel time distance? Like how do you know that?
So it's a synthetic example. It's a map showing, so I create a grid of sources. I create a grid of sources with a known velocity, some known velocity model. So I know the travel times.
Like from airstrikes, like you said, or
Here? No, I use
sources?
synthetic sources. Say, you put a source every kilometer here, and you measure the travel times. Given a velocity model, you know the arrival times at each one of the stations. And then you say, what would be the travel time misfit for a source here if I constrain its location to be here? Which is what I do in the actual study. In the study, I actually constrain the location to be along the Salah ad-Din road. So the travel time misfit here for a known velocity structure is 5 seconds. So this gives you some criteria for the quality of the location, right? If you locate a source here that you restrain or constrain to be here and gives you 5 seconds of misfit, that tells you that it's probably not coming from Gaza. This is why this is how I derive a criteria for the quality of the detections or locations.
Uniqueness of the solution.
Yes. Yep.
Suppose the Hamas now radio paper or someone, Daesh, the next attack, they want to trick you and they stagger their mobilization somehow. Will be a challenge? A higher challenge? I mean, you depend on their
Yeah, it depends on what they do on the background. If they stagger their mobilizations regularly every day, then you won't see it. But if it's different than what happens on a regular day, then you will see it. Doesn't matter how they move. Anything that is out of the ordinary would manifest seismically.
So in principle, this technology and approach be used to identify drilling, or is the noise to
Yeah, it could be used to identify drilling, but these are much smaller sources, so you have to be very close to be able to see them. Yeah. Yes.
So this is kind of a conspiratorial question. If you had a bunch of arrays of these sensors, say all around the boundary of the Gaza Strip, right? Say you spend a lot of money on putting an underground barrier, and you put a bunch of these detectors, how well would you be able to hear the attack coming? So you're pretty far away, so your noise is pretty, so the signal to noise ratio is not in your advantage. But if you're much closer and you have now tens of these sensors, how much beyond the noise level would you be able to detect this attack? And if you can do that, if it's statistically very simple to do it, how is it that this didn't trigger the sensors?
So regarding the first part of the question, the answer is yes, you would be able to see it much more clearly if you're close to the source, much factor of 10, but depends on the sensor you're using. These sensors are highly sensitive and have a very low level of self-noise, so if you're using the same sensors at those distances, and we would amplify by a factor of 10 or so, at least an order of magnitude. Plus, if you have distribution all along the fence, that you would have an excellent constraint on the location. For the second part of the question, I really can't give you an answer. So I don't know how the data are processed and if data were collected at the barrier, etc. Generally, people tend to discard the noise. The information that is being used here is considered garbage. So 99% of the records are being thrown away. And most of the time people look for impulses rather than analyze the noise. So this is a different approach to what is generally being used. Okay. I hope it answers the question.
We must finish, but you're all welcome to our almost weekend, and Asaf will be there.
Yeah.
So you can talk to him. Thank you again.
Thanks.